All right, welcome to Universal Gravitation. Let's just talk about the basics. Step one, we lied to you, okay? Because the gravity that we use is not exactly the truth. So let's talk about what the truth is. So let's draw a beautiful picture of the Earth. Earth. All right, so here's the Earth. Now, the Earth has what we call gravitational field lines. So this means that any object that has mass is going to be drawn towards the Earth. And you'll notice these lines are all straight and they all radiate exactly towards the Earth. Now, I'm going to kind of zoom in on a section here. So notice they're all equally spaced. All right. But you'll notice as we get really close to the Earth, they get very close together. And as we get far from the Earth, the spacing increases. All right. So if we look like right here, it's like they're right next to each other, but here they're a lot farther apart. And so the farther away you get from an object, then the weaker the field strength gets. Okay. And because this is in a circular pattern, it is what we call an inverse squared relationship. Okay. So the strength of the field is inversely squared to the distance away from the field. Okay, so let's then talk about what the truth is. Okay, so there was this dude named Newton, and he invented this universal gravitation. Universal gravitation. Now, everyone has the idea of like Newton and he gets hit in the head with the apple and like, oh, he's like, oh, gravity. That's not the truth. In reality, Newton saw an apple fall basically or something like that. But then he looked up at the moon and he said, wait, if things on Earth can fall, then the moon must also be falling. And that means all the stars are falling and all this stuff. So he said everything must be feeling the effects of universal gravitation. And so he looked at this. Now, he did not invent this field line stuff, that was done later. But basically, with him and then some other people combining their ideas, we came away with this relationship. Fg equals GMM over R squared. Now, this is a bit different than what we think of as universal gravitation, because when we think of when we think gravitation, we think Fg equals mg. Well, this is only true on Earth, and this is kind of true everywhere. All right, so let's talk about what all of this stuff means. So if we break this down, this G here is our gravitational constant. All right, gravitational constant. And it is 6.67 times 10 to the 11th Newton meters squared per kilogram squared. And you might be asking yourself, why is it so ugly? Well, it's so ugly because it literally exists just to make all of our made up units work together. All right. So maybe if we were smarter, there were some, official units that the cosmos wishes we had come up with. And they were like, oh, you were supposed to come up with this, and you came up with meters. Oh, well. So these are literally just there to make all the units come together. It's on your equation sheet. You do not need to memorize it. So don't worry too much. All right. Then we got some other pieces of this puzzle here. All right. So this big M is the mass that creates the field. All right, so this would be like the Earth versus something else. The Earth is creating the field. So if I were to drop a pebble on the Earth, well, the Earth is what's creating the field, and that pebble is what's in the field, and that pebble's mass would go like here. This is the mass of the object that is in the field. All right. So now, in all honesty, every single object creates its own gravitational field. But if we drop something on Earth, we don't see the Earth move towards it because the Earth is freaking huge. That's also why we usually use a capital M to denote the larger of the two objects. But, you know, it is true that every object has a field, but we always look at it from a certain frame of reference because we have to kind of pick one frame of reference for everything to make sense, one lens to look through, if you will. All right, and then this R here, this is the distance between the centers of mass. Okay, so you'll have two objects. So for example, let's say we have the sun. All right, there's the sun. And then we have the earth. This is not drawn to scale in any way, shape, or form. And we would say, okay, well, the radius is the distance between their centers. All right, so that would be the radius. Okay. And basically, it's just a plug and chug equation. Now, there is a secondary concept to this. If we kind of link these two equations together, all right, so if we get these two guys to kind of be linked together, then we can actually look for an individual object's gravitational field strength. Like this G right here, we know is 9.8 newtons per kilogram on Earth. But the question's like, well, why is that true? So I'm going to go and I'm going to show you guys how we can actually calculate the gravitational field strength for any object. So if I set these two equal to each other, then I get G mm over r squared equals mg. And you'll notice that the mass of the small object is inconsequential here. And then we're left with the gravitational field strength of the massive object is equal to this. So if you take your gravitational constant times the mass of the object, and then you divide it by the radius squared, you get the gravitational field strength of that object. And so you're probably asking, well, like, what do I use as the radius? Because don't I need two objects to measure between? Well, this radius would be kind of like the surface of the Earth. So if I was to say, well, what is the gravitational field strength of the Earth? If I was to say, well, that's the radius, I would just punch that number in there, square it, get the mass of the Earth times by the gravitational field strength, and you'll basically get your 9.8. And this also then accounts for why there's differences in gravitational field strength, because if you were, say, in a, let's see if I can draw, there's like the, there's the thing in outer space. Was it the space shuttle? There's my brain. So if you're like on the space shuttle, you're going to experience literally a different gravitational field strength because your radius is going to be a different value than that on Earth. And so it's going to be a slightly different number. But that's basically how you calculate stuff. It's really much just a plug and chug equation, and we're just going to kind of use it as we go. I'll go give you guys some example problems, but yeah, welcome to universal gravitation. Closer to the truth, still not the exact truth, but hey, it's less of a lie. So, as always, have fun in science!